Hello everyone, we will present our paper, TriVol Point Cloud Rendering via triple volumes. In this paper, we present a dense, lightweight 3D representation called TriVol that can be combined with NURF to render photorealistic images from point cloud. TriVol has two advantages. First, it fills the respective field at different scales and thus extracts local and non-local features for discriminative representation. Second, since the volume size is greatly reduced, our 3D decoder can be efficiently inferred, allowing us to increase the resolution of the 3D space to render more point details. Extensive experiments on different benchmarks with varying kinds of scenes and objects demonstrate our framework's effectiveness compared with current approaches. Moreover, our framework has excellent generalization ability to render a category of scene and object without fine-tuning. We first introduced the task setting of point cloud rendering. Given a colored point cloud, the output is required to be the corresponding photorealistic multiple view images. However, there are a lot of challenges to deal with. First, since the point cloud captured with a physical device is usually sparse, there are a large number of missing points. Thus, the rendering results often become blurred. Moreover, we need to ensure the rendering network to be generalizable to different scenes, and the rendering results should be multiple view consistent. The typical learning-based point cloud rendering strategy uses many coring methods, including the ball coring and the KN coring. However, if the current position is far away from its neighbor points, the feature extraction will usually fail. To this, some methods are proposed to employ 2D neural networks for processing. They first project points into 2D plane and then use a 2D network to shape images. However, due to the 2D processing stage, we cannot ensure the multiple view consistency. Another kind of method uses 3D networks to obey a dense feature volume. However, the computing cost is too heavy for high-resolution 3D representation, as shown in this table. Increasing the volume size will quickly cause out-of-memory issue. In this paper, we propose a dense yet efficient 3D representation called TriVol for point cloud rendering, and we design an effective encoder-decoder framework for TriVol to achieve photorealistic view consistency rendering. The following table is a comparison among different methods in terms of 3D representation, feature extraction, coring, and rendering strategy. Our proposed framework can achieve SOTA performance on the rendering of various scenes and objects as shown in the following figures. Now we will introduce our framework, and we shall first give a list of notations as shown in this figure. This is an overview of the proposed TriVol, which consists of 4 stages, including encoding to obey initial TriVol, decoding to obey the feature TriVol, and conducting feature coring in the obeyed TriVol, and using the extracted features to conduct the rendering with NURF strategy to get images. Now we will introduce them in order. Before the encoding stage, we need to voxelize sparse point cloud into grid voxels V. The shape of V is C times S times S times S, where C is the feature channel number and S is the resolution. However, due to the sparse property of the input point cloud, directly coring with V will getting meaningless values for most 3D locations. Of course, we can change sparse V into dense V using 3D components, where a lot of computation and memory resources are required, and the sparsity of V will impede feature propagation. Therefore, in the encoding stage, we change V into Vx, Vy, and Vz, and each of them is a scene volume. The encoding is conducted via a grouping operation. We first divide V into G times S, and concave obeyed n voxels in each group. Therefore, the shape of the initial TriVol is Cn times G times S, where G is much smaller than S. Such an encoding strategy has several advantages, including getting rid of huge computing resource, increasing the respective field of each group, and allowing us to extract both local and non-local features. Also, note that our TriVol is different from chiplet representation, which may lost 3D information during encoding. For the decoding stage, we use 3D units to the initial TriVol to change them into the dense representation. After getting the dense feature TriVol representation, we can carry the feature of each 3D point and then conduct the rendering. The feature querying is completed by interpolation in TriVol, and we use follow rendering enough to obey photorealistic 2D images. Especially feature querying consists of sampling and querying. For point sampling, we follow cost to fan sampling, and for the querying, we use trilinear interpolation to calculate 3 feature vectors and fuse them via concave and show in the following equations. The follow rendering is completed by setting MLP to obey the density and colors for a given position and random choose the final color as this equation. Our model is only supervised by the rendering loss, which is the reconstruction error between the random colors and the ground truth. The experiments are conducted on object level as well as scene level dataset, including ShapeNet, GSO, and ScanNet. There are 3 kinds of baselines utilized in the experiment. The first is the method which uses 3D dense units to transfer sparse voxels into dense feature representation. The second is sparse conv net that uses sparse convolution library to replace the dense unit. The third is the conv-o-net that converts the point cloud feature into the chiplet representation for 3D reconstruction. We first report the results of scene level rendering, and shown our method produces better results. And this is a quantitative point cloud rendering comparison on the ScanNet dataset. Our method produces realistic rendering results that are more close to the ground truth. And those are the object level rendering evaluation results. Our method again achieves the SOTA performance. And the quantitative point cloud rendering comparison on the ShapeNet also demonstrates the effect of our method. Also, the comparison on the GSO dataset. Moreover, we also conduct several ablation studies. First, we analyze the effects of different encoders. We can see the performance of those encoders are all weaker than our proposed grouping operations. The effects of TriVol resolution are also studied. We can see TriVol has a much better accuracy in rendering while lower computation resource requirements. The effect of point cloud number is also explored. Our method achieves the best performance with different numbers of input cloud, especially when the number of testing points is far less than the training point. Our method shows a more robust performance compared with point nerf. Thanks for your watching and welcome to our poster for discussion.